Today we're diving into Fibonacci's hypothetical cottontail farm that introduced the world to one of math's most fascinating sequences. It's more than just cute bunnies. This story connects everything from sunflowers to seashells, even galaxies, to a simple problem that was proposed in medieval Italy. Buckle up, because Fibonacci's rabbits are about to multiply their way into your mind. In the year 415, the infamous philosopher and mathematician Hypatia of Alexandria, Egypt, was savagely murdered by church monks. This murder shocked the Roman community and its government leaders. Hypatia was known far and wide as a respected philosopher, mathematician, government advisor, and a professor. Hypatia, The Sum of Her Life, is a book that I wrote that looks not just at the circumstances surrounding her death, but also at the sum of her entire life. I weave in the details of her education, disciples, Neoplatonic philosophies, female contemporaries, and the many mathematics that she wrote and taught about. There is truly more to Hypatia's life than her death. Hypatia, The Sum of Her Life, written by me, Gabrielle Burchak, is now on sale on Amazon. Buy your copy today. What do rabbits, nature's cutest fluff balls, have to do with one of the most famous patterns in mathematics? Well, imagine this. A single pair of rabbits starts multiplying, as they do, just two at first, but soon the field is hopping with Rabbit De Niros, Luke Skyhoppers, Marilyn Bunros, and Jessicas. Before you know it, you're asking yourself, how many rabbits are there? And boom, you've just stumbled into the genius of Fibonacci. Today's podcast isn't just about cute bunnies. It's about uncovering the mathematical DNA of life itself. From sunflower spirals to stock market trends, Fibonacci's thought experiment about a rabbit problem paved the way for connections that resonate centuries later. It turns out that his thought experiment turned out to be a formula for understanding nature and even our own DNA. Fibonacci was a 13th century mathematician who lived in Pisa. Actually, his name was not Fibonacci. Instead, it is recorded that his name was Leonardo. In 13th century Italy, people didn't have last names. They were associated with the areas that they were born in. So he was referred to as Leonardo of Pisa or Leonardo Pisano. The actual origin of his name is still debatable. Sources list him as Leonardo Figlio di Bonacci, which means Leonardo, son of Bonacci, or Leonardo Pisano Bigolo. One of my favorite historians, David Eugene Smith, noted that the name Bigolo was used in Tuscany and meant traveler. And this makes sense because Fibonacci's father, Guglielmo, was a customs official and an Italian merchant. As a young boy, Fibonacci traveled with Guglielmo throughout the Mediterranean coast, where he learned about the merchants and their mathematics. Then, in 1838, a Franco-Italian historian named Guillaume Libri referenced him as Fibonacci, and the name stuck. So, as he traveled along the Mediterranean coast during his travels to North Africa in the late 1200s, Fibonacci was exposed to the Arabic mathematical system, which was far more advanced than what was commonly used in Europe. The Arabs had made significant strides in algebra, decimal place value, the use of zero, and geometry, all of which had been heavily influenced by Indian mathematics. These ideas were unfamiliar to Europeans who still relied on Roman numerals and older forms of calculations. Through his interactions with Arab scholars and traders, Fibonacci absorbed these new concepts and recognized their practical applications, especially for commerce and trade. This knowledge profoundly impacted him as a kid, and he continued to refine these applications of mathematics over the years as Fibonacci incorporated these ideas into his work. Then, in 1202, at about the age of 32, he published his groundbreaking book, Liber Abaci, which means the Book of Calculation. Though the original work does not exist, a copy from 1228 has been analyzed and translated. In his pioneering work, Liber Abaci, Fibonacci introduced the Hindu-Arabic numeral system to the West. And though the original work doesn't exist, a copy from 1228 has been analyzed and translated. In this work, he explained algorithms, equations, and practical problem solving using his methods. His exposure to Arabic mathematics transformed how calculations were performed and helped lay the foundation for the modern decimal system and the Fibonacci sequence. Through his book, Fibonacci bridged the gap between Eastern and Western mathematical traditions, fundamentally shaping European mathematics for centuries. In his book, Liber Abaci, Fibonacci's Hindu-Arabic numeral system included 10 digits, 0 through 9. It used positional notation, which made calculations more efficient and manageable. In the second section of his book, Fibonacci demonstrated the practical value of these numerals by applying them to tasks like commercial bookkeeping, converting weights and measures, converting different currencies, interest calculations, and money exchange. Liber Abaci also includes information about irrational numbers and prime numbers. His work was widely embraced across Europe and significantly impacted European thinking. It replaced the old system of Roman numerals, ancient Egyptian multiplication methods, and the use of an abacus for calculations, which made business calculations more manageable and quicker. This advancement played a necessary role in the growth of banking and accounting in Europe, helping to streamline financial processes and drive economic development. Additionally, his book did more than assist in financial processing. It had considerable influence on European science and mathematics. Liber Abaci is an incredible body of work that includes one of my favorite thought experiments. Fibonacci wrote, quote, "A man has one pair of rabbits at a certain place entirely surrounded by a wall. We wish to know how many pairs will be bred from it in 1 year if the nature of these rabbits is such that they breed every month one other pair and begin to breed the second month after their birth. This hypothetical rabbit population problem introduces the Fibonacci sequence." So why did he choose rabbits? Well, because rabbits are a friendly bunch. Like, super friendly. Like, turn on the slow jazz and pour the wine kind of friendly. They are so friendly that they have the entire Barry White playlist blasting from the bushes while they make babies, who then go on to make even more babies. So Fibonacci's solution shows that, generation by generation, there becomes a sequence of numbers. The sequence is known as the Fibonacci sequence, and it's a series of numbers wherein each number is the sum of the two preceding numbers. The simplest example would be the numbers 1, 1, 2, 3, 5, 8, 13, and so on and so on and so on. The sequence starts out with the number 1. The second number is also 1 because the preceding numbers that we add are 0 and 1. So the third number is 2 because the preceding numbers that we add are 1 and 1. The fourth number is 3 because the preceding numbers that we add are 1 and 2. The fifth number is 5 because the preceding numbers that we add are 2 and 3. And on and on and on. So we just keep adding the two preceding numbers to get the next number. These hypothetical breeding rabbits showed in this sequence that the number of rabbits increased through a pattern after each generation, which, in theory, could extend to infinity. Infinite rabbits. Fibonacci also showed that as the sequence progresses, the ratio of each number to the number before it approaches the golden ratio, which is approximately 1.618. It is denoted by the Greek letter phi. So, for example, when we get to the 16th and 17th digits, which are the numbers 610 and 987, and we divide 987 by 610, we get 1.618033. The equation that defines the golden ratio is phi equals 1 plus the square root of 5, all divided by 2. The golden ratio can be applied in several ways to enhance balance, harmony, and efficiency. In architecture, the golden ratio is often used to create aesthetically pleasing proportions, as seen in the design of buildings like the Great Pyramid of Giza or the stupa of Borobudur in Java, Indonesia, which is the largest known Buddhist stupa and has the dimension of the square base related to the diameter of the largest circular terrace, which is 1.618. In art, artists like Leonardo da Vinci have incorporated the golden ratio into their compositions, such as the positioning of figures in the Vitruvian Man, which ensures a visually pleasing arrangement. Graphic designers and photographers and hobbyists use the golden ratio to create layouts that naturally guide the viewer's eyes. This results in more effective and engaging visual communication, such as in brochures or even web page designs. For my math nerds, in further mathematical advances, we also learn that the Fibonacci sequence is a second-order linear homogeneous recurrence relation with constant coefficients, which satisfies the recurrence relation. Sorry, I know that's a mouthful. In short, a second-order linear homogeneous recurrence relation is a rule that tells you how to calculate the following number in a sequence based on the two previous numbers. This specific rule involves fixed numbers, also known as constants, that don't change as the sequence continues. So here's an analogy. Imagine you are building a tower of blocks. The height of each new level depends on the heights of the two levels below it, and you're going to use a rule that tells you how to stack the blocks. The rule would say, to make the next level double the height of the one just below it, then subtract the height of the level that is 2 steps down. So, if the first level is 1 block high and the second level is 2 blocks high, you can figure out the third level. You do this by doubling the second level, which is 2 times 2 equals 4. Then you subtract the first level, which is 4 minus 1 equals 3. So, the third level is 3 blocks high. And you keep following this rule to find the following heights. So, a recurrence relation is like building a tower where you follow the rule to find the next number. On my website, I'll provide a rule with 2 distinct roots and show how the Fibonacci sequence satisfies the recurrence relation. You can find it at mathsciencehistory.com. And hey, while you're there, don't forget to click on that coffee button because every donation you make truly helps me keep this podcast up and running. So, back to Fibonacci's story. The Fibonacci sequence is brilliant because it even lends to the Fibonacci spiral. You can visualize the sequence through the Fibonacci spiral. The Fibonacci spiral is a geometric pattern approximating the golden spiral, a curve that grows proportionally as it winds outward. So let's take the Fibonacci sequence, which starts with the series of numbers 1, 1, 2, 3, 5, 8, 13. Now, draw a 1 by 1 square and then another 1 by 1 square next to it. Then add a 2 by 2 square adjacent to the first 2 1 by 1 squares. Then you add a 3 by 3 square followed by a 5 by 5 square and so on and so on. Then in each square, you can draw a quarter circle arc that connects opposite corners. So as you move from one square to the next, the arcs create a continuous spiral. I will also post an image of the Fibonacci spiral on my website at mathsciencehistory.com. And also, don't forget, while you're there, click on that coffee button, please. Donations really help keep this podcast up and running. If coffee buttons aren't your thing, you can also find me on Patreon. At Patreon, I have a variety of tiers, including a pay what you want tier. Patreon patrons also get early access to the podcast and blog. So, back to the spiral. Okay, so the spiral grows larger as it moves outward, and the shape becomes smoother and could theoretically expand to infinity. It has no end. And you can see the spiral in nature around us. It's amazing how nature is connected to the Fibonacci spiral. You can also see the spiral in an arrangement of sunflower seeds, pine cones, and nautilus shells. The Fibonacci sequence and the Fibonacci spiral are a wonderful reminder that we are all very connected to mathematics. It is in nature and around us and within us. The Fibonacci sequence and the Fibonacci spiral are evident in art and architecture, as well as the rhythm that we listen to in music. The scales on the piano reflect the Fibonacci patterns as well. Algorithms created for search functions and data structures are also based on the Fibonacci sequence. In computer science, Fibonacci-inspired algorithms play a role in efficient data organizations, such as Fibonacci heaps, used in graph optimization problems. A Fibonacci heap is a type of a data structure used in computer science to manage a collection of items, especially when you need to find and update the smallest value. For example, imagine you have a lot of files in a filing cabinet. These files have numbers or priorities, like a task with a deadline, and you want to put the files in the filing cabinet. Instead of putting all the files in a specific order in the filing cabinet, you group them into piles, each following a loose structure. A Fibonacci heap allows you to find the file with the smallest number or the lowest priority. And it's always a fast process because the file with the smallest number or lowest priority is always on top of one of the piles inside the cabinet. And when you add, remove, or change the files around, the cabinet will reorganize itself so it can still find the smallest file quickly. That's the concept behind a Fibonacci heap. Also in engineering, many designs benefit from Fibonacci patterns to optimize efficiency and aesthetics. In biology and medicine, the sequence helps researchers understand growth patterns and structures in organisms. We see the spiral in the arrangements of seeds and sunflowers that I've mentioned before, which offers insights into developments in nature. We also see the spiral patterns in our DNA, which lead us to understand potential medical applications. When you look at the double helix, the ratio of the width of the helix to its length for one complete turn is about 1 to 1.618, which is the golden ratio. So, this is so cool. Math is in our DNA. That is such a cool concept to realize. We are mathematicians down to our DNA. But while the Fibonacci sequence and the golden ratio are often celebrated as universal rules of beauty and nature, they're not as all-encompassing as commonly believed. Many natural patterns, like the arrangement of leaves or spirals and shells, are only approximations of the Fibonacci sequence, and some deviate entirely. Similarly, the golden ratio is often exaggerated in its role in art and architecture. Claims that it was intentionally used in structures like the Parthenon or the famous artworks like the Mona Lisa are speculative or even coincidental. Moreover, the Fibonacci sequence is just one example of a broader mathematical study of patterns in nature, which includes other mathematical forms like logarithmic spirals, fractals, and tessellations. While fascinating and important, neither the Fibonacci sequence nor the golden ratio holds a monopoly on explaining the complexity and mathematical beauty of the world around us. Still, Fibonacci was a brilliant man whose contributions to our understanding of math and nature continue to astound us. Fibonacci published 3 other works, including Practica Geometrae in 1220, the Liber Quadratorum in 1225, and the Flos in 1225. The Flos resulted from Fibonacci's meeting with Emperor Frederick II and his court. Through this meeting, he was introduced to Johannes of Palermo, who was also a mathematician. The emperor proposed that Fibonacci exhibit his mathematical insights by solving mathematical questions written and presented by Johannes of Palermo. So Fibonacci set forth to prove to Johannes his capabilities through the construction of his book, The Flos. He published 2 other works that were lost in the annals of history, and these include Dimino Guisa, which means On Commercial Arithmetic, and the commentary on Book 10 of Euclid's Elements. Symmetry teaches us a lot. It teaches us how balance in life, relationships, and work leads to greater efficiency and harmony. Whether in nature, art, our personal and working relationships, or our sociological structures, symmetry reminds us that finding balance is key to thriving and growing. Rabbits have this figured out. They know the importance of growth, which explains why they breed so well. So the next time you see Fluffernutter McFluffyface, Rabbit Downey Jr., or the entire bunny band Thumper Nickelback scouting the yard for their lovin' lagomorphs, Know that these rabbits are living their best lives in mathematical exploration. I wonder if that's what Fibonacci was thinking when he developed this hypothetical bunny farm and inadvertently invented a rabbit herd of algebraic romance. The bunny puns keep coming. So next time you're marveling at a sunflower, plotting Fibonacci retracements in the stock market, or just pondering the symmetry of life, give a little nod to those concupiscent cotton bottoms. Thank you for listening. Until next time, carpe diem, my friends. Thank you for joining me at Math Science History. Please remember to subscribe to the show. Also, if you could please leave a rating or a review, it would be really appreciated. Because those ratings and reviews really do help to increase my listenership, which help to get me more sponsors, which help me keep the podcast up and running. If you want to learn more about the history of math and science, please visit me at mathsciencehistory.com. If you like what you're listening to, and if you like what you're reading, please feel free to click on that coffee button and buy me a cup of coffee. Every cup of coffee that you buy helps me pay for the expenses that go into making this podcast. Also, if you're interested in leaving me a comment or chatting with me, you can always find me on your preferred social media platform, including X, Instagram, Facebook, LinkedIn, Goodreads, TikTok, Threads, etc., etc., etc. Just go to Google and search for Gabrielle Burchak. You can find me everywhere. Until next time, carpe diem.